Alright, so here's this frames problem. Reading the question, we have a spring pack consisting of 3 identical springs is stretched using the device below. Alright, if the entire spring pack is stretched 40 millimeters upon reaching equilibrium. So I want to be careful here. 40 millimeters, I'm going to go right ahead and convert that to meters. So it's going to be 0.04 meters. And it's being stretched, which means we know the force from this spring system is going to be one big force going this way. And I don't know the K's at the moment, so I'll leave that for now. So question 8, find the magnitude and location, as measured from A, of the single equivalent force that can represent the distributed load. So, this thing right here. So what we can do is we can split this total distributed load up into 2 distributed loads. One rectangular distributed load, which will be in purple, and a triangular distributed load, which will be in green. So for the purple one, because it's a rectangular load, we know that the total force from this rectangular load is right in the middle, and the magnitude of that force is just the area of this rectangle. Its height, which is, a little bit careful here, 10 times the length, 1 meter. So 10 times 1 is going to be 10. And the units are kilonewtons. For the triangular load, it's going to be the area of the triangle. That will be the strength of the total force from this green triangular load. And the placement will be over here, 1/3 of the total length of that triangle. 1/3 of 1 meter is just 1/3 of a meter. So I got the placement. The magnitude of that total green load is going to be the area of the triangle. 1/2 times the length of the base, which is 1, times this height right here. Got to be careful. This height is going to be 20 minus 10. This whole thing is 20. This whole thing is 10. So the guy that we want is going to be 10. So 1/2 times the base, 1, times 10 is just going to get us 5. 5 kilonewtons downwards. So we need to find one single force that represents this whole thing. So I need to find one single force that represents this 10 and this 5. Well, it's definitely going to be a 15. 10 down and 5 down make a total of 15 down. But where is this 15 going to be placed? Well, the 15 is going to be placed such that it creates the same moment as this 10 and this 5. So let's write that as a math equation. So the moment of our equivalent force will equal the moment of the 10 plus the moment of our 5. And we want to calculate these moments about A. So for the moment of this 10, it's going to be our force, 10, times its lever arm distance. That lever arm is going to be this distance here. And the best way to calculate that is we have half of this base right here. So that is half of 1 to make 0.5. That is our distance here. And then this is another 0.5. So 1. And that moment will be clockwise. Now for the moment of the 5 kilonewton force from that triangular load, Well, best way to do that is just, we have this entire distance right here, and subtract off of that 1/3. So it'll be 1.5 meters, which is this whole thing, minus 1/3. So that will be 7/6. And that force, like we discussed, is 5. And the moment from this triangle is also going in the clockwise direction, so I can just add both of these because they're going in the same direction. So the total moment from both these guys doing that math is going to be 95/6. Of course, the units will be kilonewtons times meters. And what we now have to say is we have to say that our total downwards force of 15 must be at some distance away from A, some moment arm distance, such that it creates this same total moment. Remember, 15 is my total downwards force from the 10, the purple one, and the 5, the green one. So we can do this math, solve for x, and we'll get 19/18, which is approximately 1.06 meters. So, just drawing this out to make sure it makes sense, here is 0.7 meters. This right here is 1.5 meters, so it's going to be somewhere in here. And that makes sense. It's kind of almost in the middle of it. Should be a little bit more over to the right side because that's where more of the force is concentrated. So this, I'll buy this. So the magnitude is going to be 15. And the location measured from A, well, I know I measured from A because I've been taking moments about A. So all my moment arms that I've been getting here are measured from this rotational point. So I know this 1.06 is measured from A. So part B, determine the reactions at C. Well, here's where I've been working. So maybe we can do a Freebody diagram on this member right here, produce some good numbers, and then work on towards C this way. So looking at that, I know I'm going to have at most two unknowns here, a force component AX and AY, and only one unknown here, because this is a roller. It can only put a force up or down, perpendicular to itself. So at most three unknowns, and I know I have three equations, some forces X, some forces Y, and some moments about a point. So I know I'll be able to produce some answers. So let me take a look at this member right here. So I'll have those two force component reactions from pin support A. I've already done some good work with this distributed load here. I know that this whole thing can be represented by a 15 kilonewton force measured 1.06 meters from A. The only other force I have is the upwards force from that roller at B. So that will be B, I'll just call it. And the moment arm, or the distance from A, will be this 0.7. And just make sure your picture is as accurate as possible. You wouldn't want to draw this 15 on the left side of B because it's farther away from A than B is. So if I do some of the moments about point A, I know I'll be able to calculate the force from that roller. So I know that B will create a positive moment. I'm going with counterclockwise is positive, B will want to rotate this member counterclockwise about A. My 15 will want to rotate us clockwise about A, so I give it a negative moment, and it's 15 times its moment arm of 1.06. And we can crunch that math, and we'll get that B will equal, it'll be 22.7, and of course the units are kilonewtons. I'm getting a positive answer for B, which, I'm really expecting, B has to be going up like this. If I get a negative number, something is really wrong here. I can now do a sum of the forces in the y direction. So here's my equation. And I can easily use it to find that AY will equal a negative 7.7 kilonewtons. So I'm getting a negative here, which means that my assumption was incorrect. My assumption being that AY was acting up. Now that's okay. This is a pin support. It can put its forces in whatever direction necessary to hold this thing steady. I'm just going to redraw my picture real quick. And it looks like AX has really nothing to balance it in the x direction. There's no other forces in the x here. Therefore, it must equal 0. Alright, and we've done everything we can with this system. So now we'll analyze this member right here. We're going to have a force from that roller going down. We're going to have a force from pin joint C. And I know that this pin joint is capable, it is able to put a force up and horizontally, but this force is a roller. It's only going to put a force, really it's going to have to be down. It can't even be up. This tension here, ropes can only pull. It has to be downwards as well. No x forces here. Therefore, this Cx must be 0. So really, I'm just going to write a Cy here, and then I'm going to write a tension T from that rope. Now, a lot of people zap right to this roller force and put a 22.7. And they are correct, but I always recommend be careful. This is one of those simple situations in which at our roller B, we only have two forces going on, the force from the top member and the force from the bottom member. Because there's only two forces, they must equal each other. So all the force that's coming from the top is given to the bottom. So it is indeed 22.7. But, and this is a big theme that I really like to emphasize when going through frames and machines, if I had another, let's say this was a joint right here, if I had some other member connecting to this joint, there would be, some other force, and we couldn't simply just do what we did. Some of this 22.7 would go here, and some of it would go here. So in this case, this wouldn't be 22.7. You'd really have to analyze this joint right here, do some forces x and y, and figure out what each one of these individual things are. So I always recommend just watch out for situations in which your junction or your joint or whatever has more than more than two sort of elements in contact with it. But in this case, we're safe with that 22.7. This is looking pretty easy. I can sum the moments about my rope point here and figure out C. Let me just get some distances in here. This is the full distance of my beam, which is going to be, looks like a 1.8. The distance from the rope to my pin C is going to be 0.5. Sum the moments about T, I'll call it. So that cy, I'm assuming it up, so it's going to want to rotate this way about point t. It's going to be in my negative rotational direction. And my 22.7 is going to want to rotate us counterclockwise, which is my positive direction. And if I do that math and solve for cy, I'll get a positive 81.72. Positive means my assumption was correct. My assumption was that cy was acting up, so I'm good there. And of course I can do some of the forces in the y now. And here that is. And I can do that math and solve for t. And I'll get a positive 59 kilonewtons. And again, I should be getting a positive because this t needs to be acting downwards. That's how ropes work. That rope cannot push up on this member. If I get a negative for this, that means some of my other work must be incorrect. So just always make sure your numbers are making sense. So we've already answered part B. For part B, the reactions at C, Cx is equal to 0, and Cy equals 81.72, and you just may want to put a little arrow showing that it's going up. Or maybe you could put positive J if you want. So next we need to figure out what's going on here. We have this T. It's that 59. So all of this is all the same rope here. So it has that, it's activated with that 59 kilonewtons of force. And then we get down here. So the way I like to think through this is that we have this 59, 59, 59, 59. And then again that same rope 59, and then we have some sort of nail here. And then we actually have a different rope going downwards. So I have 3 of these 59s going upwards, one unknown rope force going downwards. That's going to have to be 59 times 3. You get 177 kilonewtons. So this force right here in our purple rope is 177. So I'm going to do a free body diagram on this top plate right here. That purple rope is going to be pulling. Rope's going to only pull, so it's going to pull up with 177. And below that, I'm going to say we have the force from the equivalent spring going downwards. So each one of these springs, horribly drawn, are in parallel. So here's K1, K2, K3. The question says that we have 3 identical springs. So I'm just going to call them all K. They're all the same. So my equivalent spring, that one spring that represents this whole trio here, will have a stiffness of 3K. And as we know, the force of this equivalent spring will equal that equivalent spring constant times the stretch or compression of that total spring. Well, a quick sum forces in the y tells us that this equivalent force must be 177. Our total stiffness of this one big equivalent spring is 3 times the stiffness of just a single spring, and the stretch of these springs is that 0.04. So we can do this math and solve for K. So if I do that math, I'll get 1,475. The units are kilonewtons per meter. So this isn't too difficult of a problem. I've seen worse. for frames and machines problems. I'd say the hardest part is this simplification here. There's a couple places where it can get confusing or you can mess up, so just be careful. Especially when you do the split here, just remember to calculate the correct height of that triangular part of the total load. And lastly, just in case you were wondering, what's the point of this note? What does this note mean? So they're saying that assume that the top plate of the spring pack can only move vertically and cannot rotate. So here's what he's going for here. There are 3 springs in parallel attached to this spring pack. Now, springs in parallel, their forces do not necessarily have to be the same here. So because I have different forces here, different force strengths, that could cause a rotation of this plate here. But like he's saying, we're not worrying about this. But also it doesn't really matter because since each one of these springs here is identical, that means their forces are going to be the same because of course they're going to have the same stretch by virtue of them being in parallel. So for this specific problem, because these springs are identical, this note is kind of redundant here. So just wanted to explain that. Alright, hope this problem made sense. If you have any questions, feel free to post them in the comments.